Let us continue with our lecture on Fraunhofer diffraction due to single slit. Okay, so in the last lecture, we have calculated the resultant intensity due to n waves with phi as a phase difference between two consecutive waves. And from where do we get these n waves? Due to Huygens principle, we have divided our single slit into n equal parts because every point on the wavefront can act as a source for the secondary wavelets. So now let us see how our intensity modifies when we do so. So the resultant intensity which we obtained in the last lecture was R is equal to A sine theta, A sine n phi by 2 divided by sine n phi by 2. So I got the expression like this, where n are number of waves, phi is the phase difference between two consecutive waves, and A is the amplitude of each wave. Now, after getting this expression for resultant intensity, I would like to substitute something. We have seen earlier that the phase difference between two consecutive waves can also be written in terms of path difference, can also be written like this: pi by lambda. And from where do we get this expression? If you remember, the total phase difference between the first and last wave was 2 pi by lambda e sine theta. And then when I divide this into n parts, the phase difference between two consecutive waves was 1 by n 2 pi by lambda e sine theta. By taking 2 on the other side and n on the other side, I get this. So, and then this is, I have called this as alpha. Now, substituting the value of n phi by 2 is equal to alpha in the equation number 1, here n phi by 2 I can substitute as alpha. So I get, let me call this as equation 2. I will get R as A sine n phi by 2. So here you see n phi by 2 as alpha, and here in the denominator we have phi by 2. So this will be phi by 2 by n. Phi by 2 is, n phi by 2 is alpha. N phi by 2 is equal to alpha, and phi by 2 is equal to alpha by n. So this I will get as sine alpha upon sine alpha by n. Now, this we got because n phi by 2 is equal to alpha and phi by 2 is equal to alpha by n. Now, if you recall, this we have divided the slit into n parts in order to simplify our calculation. But in general, n is very large. The slit is made up of infinite number of parts. Now, when I take n very large, my alpha by n becomes very small. So alpha by n is very, very less than 1. If such thing happens, then sine alpha by n can be approximated as alpha by n. You all know that sine theta is approximately equal to theta if theta is very small. So therefore, now using this approximation in equation 3, in the denominator I will get as R is equal to A sine alpha upon alpha by n. This I can denote as equation number 4. By taking, now I can write as R is equal to NA sine alpha by alpha. A is the amplitude of each wave, and there are n number of waves. So NA I can denote as capital A, which is the total amplitude of the waves. So this is my final resultant amplitude in terms of alpha, where, and you have to remember what is alpha. Alpha is pi by lambda E sine theta. Now, if I know the expression for resultant amplitude, I can find resultant intensity. This is due to Fraunhofer diffraction due to single slit. I is equal to, and you all know that intensity is directly proportional to R square. So I get as A square sine square alpha by alpha square. This is my resultant intensity. Now you can remember that from the Young's double slit experiment, I got the intensity as 4a square cos square phi by 2. But now when I include, again I am doing the superposition of two waves, but when I include the slit width, my intensity is modified and I get my intensity as a square sine square alpha by alpha square, where alpha is this much. So this is my new expression for intensity due to Fraunhofer diffraction due to single slit. Now what is our next goal? This is earlier I have taken equation number 4, so this I will denote as equation number 5. Now let us see that how the intensity modifies, and we'll try to find the maximas and minimas, and we'll try to plot that how my intensity pattern look like in Fraunhofer diffraction due to single slit. Let us continue this in next lecture.